Well, let's kick off. Thanks everybody for listening in. I look forward to chatting with you, hopefully in the breakout room or otherwise directly. So I'm going to talk, my name is Evan Powell. I'm going to talk a little bit about container attached storage and specifically OpenEBS and how this kind of helps you operate stateful workloads on Kubernetes, including, of course, distributed SQL workloads. So just quickly, a little bit about myself. So Evan Powell, founding CEO of a company called MayaData that I'll tell you about. And you can see the agenda here. We'll also talk briefly about chaos engineering, and I'll explain why that is being used quite a bit, at least amongst our users out there as well. And we'll look at a couple of different specific workloads with some performance characteristics. And so I'll try not to speak too quickly, but we do have a lot to cover. So let me dive in. Just quickly, MayaData, we sponsor two now Cloud Native Computing Foundation projects, OpenEBS and Litmus. Litmus is the chaos engineering project. OpenEBS is the container attached storage project. We do have a commercial solution that is available as SaaS called Kubera, which gives you that overall framework for management. And it's really all I'll say about Kubera and the commercial bits here today. Just quickly, who is MayaData? So we're about 95 engineers now. We do contribute upstream, as I said, to a couple of CNCF projects and others, not just the ones that we started. And as such, we ended up becoming around the 5th largest contributor as measured by pull requests to all Cloud Native Computing Foundation projects. So we do believe in code as marketing. If you go and check out what's called DevStats from the CNCF, where they track all manner of contributions, pull requests, and the whole long tail of all of these different projects, you will be using OpenEBS because actually the CNCF itself is a reference user, and one of their use cases is DevStats. And this is one non-scientific survey. There's others out there, but the long and short of it is that OpenEBS is being used quite a bit. It's about 3.5, 4 years old now. Container pulls, which is a vanity metric, I know, are roughly running at the level of Kafka right now over the last month or two, to give you some idea. So broad open source usage. So why specifically Yugabyte and OpenEBS? This is just as an example, and this actually comes from a blog, as you can see on the OpenEBS site, which is the part of the CNCF now, as I said, contributed to them. But this blog was contributed by Jimmy from the Yugabyte team. And I think what it unpacks briefly is that, you know, if you're running a distributed SQL workload, you don't really want to spend your time worrying about pooling disks underneath, or reprovisioning and provisioning disks underneath, or cloud volumes underneath. All of that stuff is a distraction. And if you're not careful, it can become bespoke or sort of snowflake-like, depending on if you're on this environment A or this cloud B. So at the highest level, OpenEBS and similar solutions, container attached storage, kind of flatten those differences and enable you to run the same on any Kubernetes environment, including down at this lower data level. People are using OpenEBS in all sorts of ways. You can find out a lot more about it from the adopters MD, right? So these are folks who have contributed, and there's more, KPN and others, Bloomberg and what have you, who have contributed a little bit about, here's how we use it. So lots of different workloads, as you can see. So by now you may be wondering, okay, container attached storage, maybe I've heard of it or I've seen the mule, which is the OpenEBS mascot. Why don't you define what this thing is? What is container attached storage? So let me begin by talking about what it isn't, right? Maybe what it's inspired by. Shared everything storage. What is that? This is basically the mentality of your traditional storage system. All your workloads belong to me, right? These are scale out systems where all the workloads that you may be running are brought down into one system. And as such, they tend to tightly couple teams and workloads. They increase your blast radius, but they evolve for a very good reason. If you think about 10 years ago or so, workloads tended to scale up. They didn't scale out very well. And disk drives were really slow, like 150 IOPS, 140 IOPS. And so to get performance, you went across lots of disk drives, across maybe multiple nodes. And to get resilience, you did the same thing. You went across multiple nodes. Yahoo, you got all those things from shared everything storage. Well, today the world's flipped, right? Actually, striping across multiple nodes slows you down because the NVMe drive in that array may be able to pull 1 million IOPS, as an example. So striping doesn't help. And then going across multiple nodes, that actually is increasing potentially your blast radius. And again, your NoSQL workload already does that for you at that layer. So this is one reason why direct attached storage, which is just the disk, just give me the disk, is becoming so popular. And it's sort of back to the future, right? Before there was shared everything storage, everyone pulled their hair out because you were literally just going straight to the disk and you're wasting all of the capacity. It was hard to manage, and it was hard to get resilience. So let's say you did want 3 copies. How would you do that? You know, a little bit of rsync hackery, what would you do? And so as a result, what we see today is container attached storage. What container attached storage does is it says each workload, workload A, gets data layer or storage layer A prime. Workload B gets its own B prime in this case. Workload A does not depend on workload B. They communicate via APIs. They're loosely coupled. It's a wonderful thing. Why should we group their storage layer together? Why not let each of them have their own separate disaggregated storage layer? OpenEBS is not the only container attached storage for sure. There's a couple of proprietary companies out there doing this to great effect. And the basic idea is to run on Kubernetes to deliver this functionality. I mentioned an NVMe engine. I'll talk a little bit more about NVMe here in a minute, but this is back to that extreme performance, which is now becoming pretty widespread, at least in the bare metal world, but also even in the hosted bare metal world or even cloud attached disks. And OpenEBS is a little bit unique in having an engine that can really handle that NVMe type of performance. And if you want 1 million IOPS in your container, you can get it. So a picture is probably worth at least 1,000 of my words. So here it is. And you can see the orange circles here are intended to be, that's OpenEBS for you, or some other container attached storage for that matter. And what you see is, again, loose couplings, right? So DB1 may be optimized for writes, DB2 may be optimized for reads. Redis, you know, when I'm flushing to disk, I just want the writes to be dropped down. And if I'm running NVMe, you know, I want as little overhead as possible. And you also can see NetApp or AWS being connected via CSI. And that's kind of a key point here, right? CSI has really enabled container attached storage by enabling a common sublayer so that we as a consumer of either bare metal sitting there or cloud attached volumes or array attached volumes via CSI, we can give you that commonality without the lock-in and without the blast radius of depending only on one or the other of these underlying environments. What we and others do via open source projects like Valero, and also as a part of our commercial offering, is we enable you to do per workload backups, right? So now that the world is so much more dynamic and you have small teams owning each workload, why not give them the granularity to manage their backups as well? And again, OpenEBS isn't the only project that enables per workload backups, and there's a variety of commercial vendors who have started to see this. They tend to be new startups because it's a very different architecture than traditional backup and data protection. Some workloads, you don't want no stinking backups, that's fine, but you get to decide now on a per workload, per work group basis. So just one quick digression. Why can't I just use the $1 million array we've already spent $1 million for, and we already have sitting there in the data center? Well, you can. But just keep in mind, you're funneling down all the IO, which could be very different patterns, into one system. And you're now tightly coupling. So part of the beauty from a Conway's law perspective of loose coupling is, done right anyway, is fewer meetings. Well, now if you all have to argue over how you're going to configure the shared storage thingy, there's going to be meetings and there's going to be discussions. You can do it, but what we see instead is a lot of direct attached storage. And it may bear, if you want to geek out on it, may bear repeating or just considering what's inside that SAN anyway. I mean, what is Sept, as an example? It's actually an amazing piece of engineering that does a lot of what Kubernetes does, or does a lot of what distributed NoSQL type system does. It keeps track of where can I store the data. It's got a metadata system. It has retry logic. It has a way to, of course, provision. All of these things were written for these scale-out storage systems years ago. And as a result, they do the job, but they do it in a way that is quite a bit different than a solution like OpenEBS or CAS, which is written on Kubernetes and turn over the management of metadata to Kubernetes as an example, or rely on retry logic from Kubernetes itself. Just conceptually, this is kind of where a project or something like OpenEBS fits. It's fitting in between your workloads and your Kubernetes engine, as you can see here. And you also notice there's OpenEBS and then some weird names under that. What are those? So OpenEBS really has embraced as a project microservices. And as such, it has multiple different engines within it. So if you really just want to get to the disk, but you want OpenEBS to manage inventory, where can I store stuff, and maybe some pooling, you might want to use local PV. Or if you have NVMe, you might want to use MayaStore. And it gives you some idea that OpenEBS itself is a project that has multiple storage engines in it. Kubera, I already said I wouldn't be talking about. Any Kubernetes and 100% user space is, we think, quite important. OpenEBS runs in the user space. So this means you just bam, deploy any Kubernetes or any fork of Kubernetes, what have you, K3 and so forth. It just works. There are no kernel modifications required. You do need iSCSI. Depending on the storage engine, you need iSCSI. So why would you use chaos engineering? Well, we actually developed Litmus originally as almost a means of self-defense, because we thought that, hey, if Kubernetes is becoming your data layer and it's changing, and these distributed workloads are themselves being rescheduled, how can you as an operator really gain confidence that my workloads and my overall application are going to hit the SLOs or service level objectives that I'm signed up for? And so a pattern I think we're all increasingly familiar with is use of chaos engineering. So we do sponsor the Litmus Chaos Engineering project. It's not just the code. We also contributed the hub. And so you can go to the hub and see, a gazillion experiments, which are basically deployed via Helm. So very easy to get up and running, really very open community, open governance. Again, it has been contributed to CNCF. And there's bigger companies helping contribute and maintain the environment. For example, I believe, I know Intuit is one of the maintainers who's contributed in Argo, and I believe there's a NetApp maintainer and others. So it's an open community, very vibrant. You can get up and going on doing some chaos engineering very quickly with the help of Litmus. So let's talk in the next 5 to 7 minutes or so a little bit about architecture. So pop the hood a little bit, if you will, and see what's there. So again, choice is good, we think. OpenEBS is not monolithic. You have multiple different storage engines. So it depends what you want to do. Same orchestration, same ability to manage the underlying disk, all of that. But you may want to just get straight to the disk, maybe via raw block. And this is stuff the community is very good at helping people with figuring out. Or you may want to use pooling on local drives. But you want that done down at that level, not up at the Kubernetes level. That's fine. You can use something as an example, ZFS local PV, or actually you sort of want a mini NetApp. Maybe you want clones, you want snapshots, you want 3-5 replicas for some sort of workload that is not super resilient, and you really want to protect it across multiple AZs. That is where CStore tends to fit. So you've got multiple choices here. And here's how one approach looks. So this is a distributed app like a NoSQL workload. And as you can see, what's happening here is OpenEBS is just helping manage access to the block device or to the host path, or maybe again to local ZFS or LVM. How this looks a little bit more under the hood. Again, a few different options there. You can see OpenEBS is there doing PV, responding to persistent volume claims. And it's the dynamism, the enhanced dynamism of this approach versus simply using local PV provisioner from Kubernetes that a lot of people really like. Because once you set up your storage classes and point those towards OpenEBS, we can do a lot, if not all, depending on the environment, of the underlying provisioning as necessary in a dynamic way, as opposed to having to pre-provision a bunch of pools, a bunch of disks. Not fun stuff to do. Why not let software do it? That's the kind of thing that OpenEBS can do for you. One point, quick point on sort of an explanation of less is more, an NVMe. So all storage systems to date, basically, use the thing on the left, if you will, that stack. I'm sure there are major exceptions like InfiniBand itself or the old fiber channel and so forth. But typically that is what you've got going, and usually there's a file system above the block layer between that and the app, actually. Doesn't matter. But the short of it is lots of hops and lots of interruptions. And what does that mean? It means slow. And so as a result, you have this mismatch in the world today where you've got NVMe and other solid state devices that are really fast. And until the NVMe protocol emerged, they were having to then basically run up the stairs, right, through all of these different transitions to get up to the actual IO and back down. And as such, they were really slow. So a couple years ago, we started on a Rust-based engine that is called MayaStore, and it has reached beta just very recently. And it's got a bunch of users now, and it can deliver literally 1 million IOPS or more to a container if you so choose. Very low single-digit overhead, 1%, 2% type overhead, as opposed to 50%, 60% type overhead for your traditional storage, shared storage. This is a C-store-like pattern. And this is one where you want the PV itself to be replicated across a few nodes, maybe across availability zones. That's also available from OpenEBS. And then we're using quorum protocol underneath to keep track of these replicas. So this is possible within OpenEBS as well. These are a couple of the, including MayaStore, the new Rust-based engine that I talked about, engines that do this for you. And this is how it looks. It should look strikingly similar. You do have an iSCSI target in this case, which can slow you down unless you're in a native NVMe environment. So when we talk about slowing you down, what are we talking about here? So this actually came from an engineer in the community, Jakob, who tested different flavors of OpenEBS and other projects on Azure. And what he found was OpenEBS MayaStore was very fast, given it's a relatively slow underlying disk. And OpenEBS with lots of resilience, which is the one sort of the third from the right, or the left, is pretty slow. And we're proud of that. We're proud of that variance or the granularity of control that this implies within the OpenEBS project. What does it really matter though? I mean, it begins to matter when you get up to the actual transactions, right? And this is actually from another big user, Second Quadrant, I believe. They're a big Postgres shop, a set of experts based out of Europe who tend to recommend the use of OpenEBS under Postgres. And you can see some of the trade-offs here. So as a reminder, to let you go, container attached storage, what is it? It really enables you in a Kubernetes friendly way to have just enough storage. And that could be like almost no storage. Just get me to the disk in a direct attached storage way, but help me use Kubernetes to manage that underlying disk so I don't have to be the one provisioning this, dealing with it when it fails or when my volume it disconnects in the case of some cloud volume. And so that's really what we're talking about with container attached storage. Seeing Kubernetes not just as something to serve, some workloads to serve, but a platform upon which systems like disaggregated storage can be built. That's the container attached storage pattern, and it fits really nicely in with distributed SQL. And with that, I'd just say try it out. Code is marketing. They're pretty active communities, both OpenEBS and the Litmus Chaos community. And then there's a third community that I'll mention that we help support, but what it is the Data on Kubernetes community, and I know Yugabyte has spoken there. I know folks from the Kafka community, Redis community, and others. Actually, MayaData has not spoken there because we really want it to be very much about what about my operators? How am I dealing with resilience? What do I do to warm back up my cache when Kubernetes kills a node? Is that even a thing I can do? That was something that a Percona expert was talking about last week, in fact. So if you want to check out a cool community to kind of compare notes about running data on Kubernetes, take a look at that link. And if you want to check out the code, take a look at openebs.io and Litmus Chaos, as you can see. Yeah, thank you. I look forward to staying in touch and communicating I didn't put I'm at ePowell101 on Twitter, or you can find me on any of these communities as usually ePowell101 or Evan Powell. So thank you.